So we were discussing about binary trees, types of binary trees. Uh, Mainly, we can define three types of binary trees: strictly binary tree, complete binary tree, and almost complete binary tree. So, what are strictly binary tree? Strictly binary trees are also called two tree and sometimes also called extended binary tree. So, strictly binary tree or two tree or extended binary tree. The definition is if every non-leaf node in a binary tree has non-empty left and right subtrees, then such a tree is called a strictly binary tree. Non-leaf means internal node. So a node which is not a leaf node is non-leaf node. If every non-leaf node in the binary tree has non-empty left and right subtree, then the tree is called a strictly binary. So if every internal node has a left and right subtrees or left and right child, right? So if every internal node has both left and right children, then the binary tree is called the strictly binary. Okay, so it means that there is no node in the strictly binary tree for which there is only one child. Okay, so it means that there are leaf nodes which have degrees equal to 0, and there are internal nodes which has exactly two children or degree equal to 2. There is no node which has degree equal to 1 in strictly binary tree, right? So that's the point second. So all of the nodes in a strictly binary tree are of degree 0 or 2, never degree 1. So in the strictly binary tree, we have internal nodes. Okay, for example, in this strictly binary, this is strictly binary. So these are the internal nodes A, B, C, and D. And if you find the degree of these internal nodes, the degree is 2 for each of the internal node, right? And if you find the degree of all the leaf nodes, obviously the leaf nodes has degree equal to 0. Okay, there is no node in this strictly binary tree which has degree equal to 1. Okay, so simple definition of the strictly binary tree is that if all the internal nodes has degree equal to 2, has exactly 2 children, and all the leaf nodes has no children or degree equal to 0, then the binary tree is called the strictly binary tree. Okay, it is called two tree because all the internal nodes has exactly 2 children. Okay, it is also called extended binary tree because the leaf nodes in the strictly binary tree can be seen as the extended nodes having no children, right? Okay, an important property of the strictly binary tree is that a strictly binary tree with n leaf nodes always contains 2n minus 1 nodes. Okay, so if there are n number of leaf nodes, then the total number of nodes in the strictly binary tree is 2n minus 1. Okay, so proof is very simple. Okay, so say b is the number of branches or the number of edges in the strictly binary tree, and we say that n0 and n1 and n2 are the number of nodes with degree equal to 0, 1, and 2 respectively. Okay, so obviously if the tree is a strictly binary tree, then n1 is 0 because there is no node having degree equal to 1. So n1 is equal to 0. Okay, so the number of branches is equal to n1 plus 2n2 because a branch or an edge emanates from an internal node. Okay, so b is equal to n1 plus 2n2 from a node having degree equal to 1, only one edge emanates, and a node which is of degree 2, okay, has two outgoing edges, right? So we have b is equal to n1 plus 2 n2. We have already discussed this in the previous lecture. Okay, so n1 is 0 for the strictly binary tree. So we have b is equal to 2 n2. This thing. B is equal to 2 into n2. And you also know that the number of branches is 1 less than the number of nodes. So b is equal to n minus 1 or b plus 1 is equal to n. Total number of nodes in a strictly binary tree is equal to n0 plus n2 because n1 is equal to 0, right? So now you put the value of n from this equation into this equation over here, and sorry, you put the value of n from this equation into this second equation, and you put the value of b from the first equation into the second equation, right? So you will get 2n2 plus 1 is equal to n0 plus n2. Okay, so you have n2 is equal to n0 minus 1. So number of nodes with degree equal to 0, sorry, the number of nodes with degree equal to 2 is equal to number of nodes with equal to 0 minus 1. Okay, that is the number of internal node is 1 less than the number of leaf nodes. N0 is the number of leaf node and N2 is the number of internal nodes in a strictly binary tree. The total number of nodes n is equal to n0 plus n2. So n naught plus n naught minus 1 or 2 n naught minus 1. Right. So in a strictly binary tree which has n leaf nodes, we will have 2n minus 1 total number of nodes. So it's an important property of a strictly binary. Now, second type of binary tree is complete binary tree, which is also called full binary tree. A binary tree is called complete binary tree if at each level we have maximum number of nodes. If at each level we have maximum number of nodes, okay, and you know that at level L we can have at most 2 raised power L number of nodes, right? So in a complete binary tree at level L, we have 2 raised power L number of nodes. That is the maximum number of nodes. Okay. So for example, this is a complete binary tree. The level number of level of this tree is 3, 0, level of loop node, then the first level, then the second level, and then the last level is level 3. Okay. So depth of this tree is 3 because the depth is the same as the level of leaf nodes. Okay, so level of leaf node is 3, so depth of this tree is 3, right? So you can see that at each level of this tree, we have maximum number of nodes. At level 0, we have maximum number of nodes to raised power 0, that is equal to 1, which is the root node. Okay, so then at the first level we have maximum number of nodes to raised power 1, that is 2, node B and C. Then at the second level we have to raised power 2 number of nodes, which is the maximum, D, E, F and G. And at level 3 we have 8 number of nodes, that is 2 raised power 3. Okay, H, I, J, K, L, M, N, O. So at each level of this tree, we have maximum number of nodes. So this binary tree is complete binary tree. Complete binary trees are also called full binary tree. Now, third type, almost complete binary tree. An almost complete binary tree is a binary tree in which at every level, except possibly the last, is completely filled. Okay, that is every level except possibly the last is completely filled, and all nodes at the last level are as far left as possible. Okay, so for example, this almost complete binary tree, the left one. Okay, all the levels except the last level. This is the last level. Okay, so level 0, level 1, level 2, level 3. The third level is the last level. So we have maximum number of nodes up to the penultimate level, up to the level 2. Okay, so the binary tree up to the last level, sorry, up to the penultimate level is a complete binary tree because we have maximum number of nodes up to the penultimate level, right? But at the last level, we don't have maximum number of nodes. Okay, so the last level might have less than the maximum number of nodes, but all the nodes are as far left as possible. Okay, so here in this example, we have two nodes at the last level, H and I, and these two nodes are as far left as possible. Okay, so see this example, the second one. Okay, so the binary tree up to the penultimate level is a complete binary tree, but the number of nodes in the last level is less than the maximum number of nodes at the last level, right? So this is an almost complete binary tree because the nodes at the last level are also as far left as possible. Okay. So what does it mean by as far left as possible? Because if all the nodes are at the left hand side of the tree, it is called as far left as possible. Okay, and the formally you can say that if for a right child at the last level, not if, you can say that for a right child at the last level there is always a left sibling, but for a left child at the last level there might not be a right sibling. Okay, there should be a sibling, right? So for example, you can see that this node J, okay, this is the left child. Okay, so this is the left child, so there might not be a right sibling or not. In this example, there is no right sibling. But if there is a left child at last level, there must be a right sibling. Okay, so for example, here H is a left child at last level, so there is a right sibling I. Okay, sorry, I just uh, mistaken here. So this says if there is a left right child, sorry, if there is a right child at the last level, leaf level means the last level. If there is a right child at the last level, there is always a left sibling. Okay, so I is the right child. So if I is a right child, then there must also exist a left sibling of it, and that is the node H. Node H is the left sibling of I. Okay, and if there is some left child at last level, then there might not be a right sibling. Okay, that's the example is the node J. Node J is the left child, and you see that there does not exist a right sibling of it. Okay, so basically this is uh, just a necessary condition for a almost complete binary tree. This is only a necessary condition. This is not a sufficient condition. Okay, it means that not a sufficient condition means that if a binary tree satisfy this condition, Okay, this one. If binary tree satisfies this condition, then you cannot say that the tree is an almost complete binary tree, because this is just a necessary condition, not a sufficient condition. Okay, so it means that if you know that this tree is an almost complete binary tree, then this condition will be satisfied, right? So this is the definition of almost complete binary tree. Okay, an almost complete binary tree and also the complete binary tree obeys the following properties with regards to its node numbering. Okay, that is the nodes of a complete binary tree and the nodes of an almost complete binary tree can be numbered in this fashion. Okay, you can number root of the tree as node number 1. Okay, then left child of the root is numbered 2 and the right child of the root is numbered as 3, right? Then the number 4 is given to the leftmost child at the second level. Then the number 5 is given to the next node at that level, at the second level, and then number 6 and so on, right? So it means that the simple thing is that you give number 1 to the root node, okay, then 2 and 3 to the left and right children of the root node, okay, then you start giving numbers at the next level from left to right, okay. So at each level you assign numbers from left to right: 4 5 6 7, okay, then 8 9 10 11 12 13 14 15 and so on, right? So in this way you can see that, so if here you can see that one is assigned to root node, okay. So what are the number of its children? 2 and 3, okay, and 2 and 3 means 2 into 1 and 2 into 1 plus 1, right? One is the index of or the number assigned to the root node. So in general, if I is a number assigned to any node, then 2i is the number assigned to its left child and 2i plus 1 is the number assigned to its right child. Okay, so 1 is assigned to the root A, so its left child B is assigned number 2, 2i, and right child is assigned number 3, 2i plus 1, right? For the node B, you can see that its number is 2, okay? So its left child is assigned number 4, 2 into 2, 4, and right child E is assigned number 5, 2 into 2 plus 1, okay? For node C is at the location, no, node C is assigned number 3, okay? So the assigned number to its left child F is 2 into 3, 6, right? So if a parent node has a number I, then its left child has a number 2i, okay. 2i is less than equal to n is the total number of node in the binary tree, and if 2i is greater than n, then I has no left child, right? So if the index is greater than the number of node, it means there is no left child. Likewise, if parent node has a number I, then its right child has the number 2i plus 1. Okay, if 2i plus 1 is greater than n, then I has no right child. Okay, if you know the number of the node, then you can also find the number of its parent. That's if you divide the node number by 2, you will get the node number of its the parent. So if a child node left or right has a number I, then the parent node has the number floor of I by 2. Okay, and that's true if I is not equal to 1. If I is equal to 1, then I is the root node, hence has no parent. Okay. So if I is equal to 1, it means this is the number of the root node and root node has no parent. And if is I is not equal to 1, then the parent node number will be found using this formula, the floor of I by 2, right? So for example, for node D, the number of node D is 4. So what is the number of its parent? 4 by 2, that is 2. Okay. And what is the parent of node E? The number assigned to node E is 5, right? So 5 by 2 is 2.5. Take the floor of 2.5, it's 2. So parent B and number is 2. Okay. Node C, the number assigned is 3. Its parent number will be floor of 3 by 2. 3 by 2 is 1.5 and floor of 1.5 is 1. That is the root node A. Okay. Now, skewed binary tree. Another type of binary tree, a binary tree which is dominated by left child or right child, is called skewed binary tree. Okay. Or more specifically, left skewed binary tree or right skewed binary tree. So, skewed binary tree are of two types, left and right. Okay, so this is an example of left skewed binary tree. Okay, so this tree is dominated by the left children. Okay, so another definition of the left skewed binary tree is that if all the internal nodes has only left child. So in this tree, there are three internal nodes A, B, and C, and each of these three internal nodes has only one left child. A has one left child. Sorry, obviously, there will always be only one left child. What I mean, the internal node has only left child. There is no right child for the internal node. So A has only left child. There is no right child for A. B, another internal node, has only the left child, no right child. C, another internal node has only left child, no right child. And D is the leaf node. Okay, so this is left skewed binary tree. In the right skewed binary tree, every internal node has only right child, no internal node has left child. So this is right skewed binary tree. So you can see that the left skewed and right skewed binary trees has linear structure. Okay, they has linear structure, so they can be well implemented using a linear array or linear linked list, right? Now, operation on binary tree. When you define a binary tree using abstract data type ADT, you specify its format specification, okay, and then you specify the operations which can be performed on the specified format. Okay, so what operations can be performed on a binary tree? So assume that you are given a binary tree T. So a long list of the operations which can be performed on tree T can be identified. Some of them are given here. This list is not exhaustive. You can also identify some more operations. Okay, these are the most frequently used operations which are performed on a binary tree. Okay, so let's see one by one. Okay, father and T. Okay, father means parent. So father and T return the parent node of the node N in tree T. If N is the root node, then null is returned because root node does not have the parent node. Okay, so left child of node N in tree T return the left child of the node N in tree T. Okay, and it returns null if N does not have a left child. Likewise, right child NT return the right child of a node N in tree T, and it returns null if there is no right child for node N. Info and T return information stored in node N of tree T, content of the node, right? The node N might be the node name, or the node number. Okay, so info nt returns the value stored at the node n. Sibling nt return the sibling node of node n in tree and return null if there is no sibling. Okay, sibling means those nodes which has the same parents are called sibling. Okay, so if the node is the left child, it will return the right child of the parent node. If the node is the right child, then sibling nt will return the right child of its parent node. Sorry, left child of its parent node. Okay, root t will return root node of the tree. Okay, if and only if the tree is non-empty. Remember, binary tree can be empty. Okay, so if the tree is empty, the root t will return null. If the binary tree is not empty, then the root node of the tree will be returned. Okay, size t, return the number of nodes in the tree t. Make empty, create an empty binary tree t. Set left st. Okay, so set left st, here t is the tree and s is a subtree. So attach the subtree s as the left subtree of tree t. Okay, and set right st, attach the tree s as the right subtree of the tree t. Okay, so in fact these two operations also requires where the left or the right subtree will be attached. Okay, you also require the location of the node n, where the subtree s will be attached as either the left subtree or the right subtree. Okay, so both these operation also requires the location of node n in the binary tree t. Okay, the last three operations are related to the traversal of the binary tree: pre-order, post-order, and in-order. Okay, so a binary tree can be traversed in several different ways. Okay, so the most popular one are pre-order, post-order, and in-order. We will discuss these traversal methods in the next few lectures. So pre-order tree traverses all the nodes of the binary tree in pre-order. Post-order traverses all the nodes of binary tree T in post-order. And in-order traverses all the nodes of binary tree T in in-order terms. Right. So these are some of the operations which can be performed on the binary tree. This is not exhaustive. You can identify some more operations which can be performed on the binary tree. Now we talk about the representation of binary tree in the main memory. Okay, so you know that a binary tree, which is a complete binary tree or an almost complete binary tree, can be numbered using the strategy that if you know that if you assign number I to some node, then its left child is assigned number 2i and right child will be assigned number 2i plus 1. Okay, so using these numberings, you can store the binary tree in the array, and that representation is called the sequential representation. Okay, sequential representation is sometimes also called array representation by the binary tree, because an array is used for storing the binary tree, right? So if the node number is I, then 2i will be the number of the left child and 2i plus 1 will be the number of the right child, right? And the node number of the parent will be the floor of I by 2. If I is not equal to 1, if I is equal to 1, it means that node is the root node. Okay, so now see this example. So this is the binary tree. 45 here is the root node. Okay, 22 is its left child, 77 is its right child, 11 is the left child of 22. Okay, and 11 does not have any left child, but it has right child 15. 30 has left child 25, but it has no right child. 77 has no left child, it has right child 90. 90 has left child 88, but it has no right child. Okay, so you can number them. So how will we number them? Okay, 45, the root node is given number 1, then 2, 3, okay, then number 4 is assigned to node 11, then 5, okay, the number 6, where the number 6 will be assigned. You can see that, okay, we assign numbers from left to right. Okay, now this is not a complete binary, this is also not an almost complete binary tree. So when you assign numbers to a binary tree which is not a complete binary tree and also not an almost complete binary tree, okay, uh, you must be careful. That is, you must assign numbers to the null nodes. Okay, here you can see that the left child of 77 is null. Okay, so when we number binary trees for the sequential representation, we also assign numbers to null nodes. Okay, so we assign 6 to this null node, which is the left left null child of 77. Okay, and 7 is assigned to 90. Okay, then 11 has a null left child. Okay, so 8 is assigned to this null left child of 11, then 9, then 10. 11 is assigned to the null right child of 30. Okay, then 12 and 13 will be assigned to the null left and right child of the null left child of 77, right? Then 14 is assigned to 88 and 15 is assigned to the null right child of the 90. So what are we are basically doing? We complete, we make this binary tree a complete binary tree by adding none nodes, by adding null to every missing node in this tree. Okay, and then we assign numbers. So to assign numbers, what you do, first you make the binary tree a complete binary tree by creating all the missing nodes, by creating null nodes for all the missing nodes, right? And then you assign numbers from left to right at each label. Okay, once you have assigned number, you can create an array of size equal to the last number of the rightmost leaf of the binary tree. The number of the rightmost leaf node is 15. So you require at most 15 cells. So you require an array of size equal to 15. Okay. So you can create an array of size equal to 15 or size having more than 15. So here in this example, we have an array of size equal to 29. Okay, so to represent this tree, we require a size equal to 15 or more. Okay, so root is stored at location 1, right? Then its left child is stored at location equal to number assigned to that node, that is 2. Okay, then the right child of root, which is 77, is stored at location 3. Okay, and so on. Here you can see that at location 6 we have nothing stored because at the number assigned, sixth number is assigned to a null node. 7 is assigned to 90, so at location 7 we have 90. Okay, number 8 is assigned to the null node, so at location 8 we have nothing. 9 is assigned to 15, so at location 9 we have 15. 10 is assigned to 25, at location 10 we have 25. 11, 12, 13, these are assigned to the null nodes, so all these locations are empty. 14 is assigned to node 88. Okay, so at location 14 we have 88, and all other locations are empty. Okay, so this is sequential representation. Okay, so another example. Okay, for this node, okay, so you number them 1, 2, 4, 5, 10, 11. Okay, how to number them? You make this tree a complete binary tree by creating null nodes for all the missing nodes, and then you number at each level, you number the nodes from left to right. Okay, and then you can create an array of size of at least size which is equal to the node number of the rightmost leaf node at the last level. Okay, and then you can store each node value at the location assigned to that node. Okay, so in this scenario, in the sequential representation, the root node will always be stored at location 1. Okay, then left child of every node will be stored at location 2i if I is the location of the node, and right child will always stored at location 2i plus 1. Okay, so here the location of A, the root node is 1, so A is stored at location 1. B is left child, will be stored at location 2 because 2 into 1 is 2. Then C will be stored at location 4, 2 into 4. Okay. D will be stored at location 5, 2 into 2 plus 1. Okay. And where E will be stored, E is the left child of D. So 2 into 5. So E will be stored at location 10. F is the right child of D and location of D is 5. So F will be stored at location 2 into 5 plus 1, that is 11. That's all. And all other locations will remain empty. Okay. So sequential representation requires a tree, sequential representation of a tree, of a binary tree with depth is equal to D required an array of size to its power D plus 1 minus 1. Right? So depth D is 3, depth D means the number of levels in the tree is D. Okay. So at the last level we have to its power D nodes, and the total number of nodes will be 2 raised power D plus 1 minus 1. Okay. So if the depth of the tree is D, then the total number of nodes in the binary tree is 2 raised power D plus 1 minus 1. So we require an array with 2 raised power D plus 1 minus 1 number of cells. Okay, so you can see that in the sequential representation, a lot of speed gets wasted. Okay, for example, consider this left skewed binary tree. The depth of this tree is 0, 1, 2, 3, 4. The depth is 4. The max level of this tree, 4. Okay. So how many cells you will require? 2 raised power D plus 1, that is 2 raised power 5 minus 1, 31. You require an array of size 31. Okay. So 31 cells will be created, and how many nodes will be stored? 1, 2, 3, 4, 5. You will store only 5 nodes in the array of 31 cells. Okay, and remaining 31 minus 5, that is 26 cells remain empty. So 26 cells will be unutilized, will be unused, right? So all the cells are utilized if the binary tree is complete binary tree, or at least almost complete binary tree. For example, this is an almost complete binary tree, okay, and this is the corresponding sequential representation, and you can see that all the cells are occupied. A, B, C, D, E, F, G, H, I. All the cells are occupied. Okay. But if the tree is not a complete binary tree or not an almost complete binary tree, then there will be several empty locations, right? So the disadvantage of the sequential representation is that a lot of space gets wasted. So what is the solution? Okay, the solution is use some kind of linked representation. So in the linked representation for the binary tree, we define three arrays: info, which stores the value of the node of the binary tree; the left and the right, which points to the left and the right child of the node. Okay. So in the linked representation, each node n in the binary tree corresponds to a location k, okay, such that info left and right are three arrays. Info k contains the data at node n. Left k contains the location of the left child of node n, and right k contains the location of the right child of the node n. Okay, and we have one special root variable or root pointer which points to the root of the binary tree. So this is the linked representation. An example, say consider this binary tree. The binary tree, in this binary tree, each node is, in each node we have also shown the left and the right children, the location of the left and the right children. Okay, so we have this spatial pointer or spatial variable root which points to or which store the location of the root node. A is the root node. Okay, so A is the information of the root node, and this is the location of its left child, and this is the location of the right child of the root A. Okay, so this is the location or the pointer to its left child. Okay, so B is the info stored at the left node of the root A. Okay, and this is the location of the left child of node B, and this is the location of the right child of node B. Okay, so at every node you can see that we have three part: the information part, the location of the left child, and the location of its right child. Okay, leaf node does not have any left or right child, so you can see that the left and right location of every leaf node is null. Okay, here cross means null. Okay, so you can use three arrays to store this binary tree in the memory: info, left, and right. Okay, info, left, and right. So root is the special variable which stores the location of the root node. Here it is 5. So at location 5, we have stored the information regarding the root node. Its information part is A. Okay, and the location of the left node is 10, and location of its right child is 2. Okay, so location 10. This is location 10. Okay, information part is B. Okay, so this is the left child of root A. Okay, now location of the left child of node B is 18. Okay, so 18, here you have node D. Node D is the left child of node B. E is the right child of node B. Okay, node B at location 10 and the location of the right child is 13. At 13 we have node E, right? Okay, node F. F is the left child of E and E is stored at location 13, right? So location of this left child is 12, 12. At 12 we have node F, okay? Node F is a leaf node, does not have any left or right children. So left and right location for node F is null, 0. 0 means null. Okay. So in this way, you can use three arrays: info, left, and right. Okay, for the linked representation of the binary tree. The advantage is that you know you require exactly as many location as the number of nodes, right? The disadvantage is that you require three arrays: information and left and right. You requires two extra pointers for each node, left pointer and the right pointer. Okay. One array, the info array, is required for storing the information. Left array is required for storing the pointers to the left children, and the right array is required for storing the location of the left children. Okay. So disadvantages: two extra arrays are required, left and right. Advantages: only as many nodes will be created as the number of nodes present in the binary. Okay, C representation of the binary tree. Okay, so this linked representation uses arrays. Okay, you can also use pointers, C pointers for the linked representation, and the structure is like this. You define a structure, struct B node. B node is for the binary tree node. Okay, then information part. In this example, the information part type is int, so int info. Then you define pointers to another binary tree node. So the statement will be struct B node star left. Okay, so this is a pointer to the left child of the binary tree node, and struct B node star right. So this is right is the pointer to the right child of the binary tree node. Okay, so struct B node star root is equal to null. So this statement will create a binary tree. This statement will create an empty binary tree with root pointer pointing to null. Okay, how will you create the binary tree? Binary tree nodes. You can use malloc and calloc statement. Okay, so using malloc or calloc, you can create the nodes for the new binary tree nodes. Okay, and then you can adjust the pointers. You can adjust the left and the right pointers.